Well, let's do one more proof of the Pythagorean theorem. This is one of my personal favorites. It's also one of the oldest proofs. It comes to us from a couple centuries before the Common Era, and it first shows up in a Chinese manuscript. And underneath the manuscript, there's only one word of exclamation, and that word is behold. So we'll call this our behold proof of the Pythagorean theorem. Okay, so let's just make sure that we understand what it is we want to show. So what we want to show is if we have a right triangle with sides length A, B, and C, where C is the hypotenuse. That's the conditions. That there's a necessity that A squared plus B squared equals C squared. So that's what we'd like to show. So we'll go ahead and start this proof by the unusual act of just building two squares. So we'll go ahead and build two squares. I'll go ahead and put my square corners in here. Two congruent squares, I should say. Square. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6, 7, 8, 9, 10. One off. Right here. Go ahead and build that square there, and then I'll build one right next to it that's congruent to it. And here's the way the proof goes. The idea is if you start at one of the side lengths of the square and just pick a location, and it works really well if you do this on grid paper. And of course, you could copy it with a compass as well. So I'll pick, since I've picked a square that's 10 by 10 on my grid paper, I'll pick the position 7 and go ahead and throw a dot in or a point in at the position of 7 away from that corner. And then do the same thing on all sides, so 7 away from this corner, 7 away from this corner, 7 away from this corner. And then you form the vertices of a new figure, a quadrilateral, I guess we could draw on the interior then of the square that we started with. And that new figure, of course, is surrounded by right triangles, which are all congruent because of the way we picked it. Of course, the way we picked it was picking this side congruent. But since those sides are congruent, what's left is also congruent. So these are all congruent triangles. And they're right triangles, so we could say that this is A and this is B. And this would be C. That's A, that's B, and C. A, that's B, and this is C. A, B, and this is C. We also should note that it looks like there's a square in the middle, and maybe we should justify that, make sure that that's a square in the middle. So if I call this angle 1 and this angle 2, then angle 1 and 2 will be here and here, 1 and 2 will be here and here, 1 and 2 will be here and here. And one of the things that we can say about the angles, the non-right angles of the right triangle, so the two non-right angles of a right triangle, is that they're complementary. Because in the right triangle itself, of course, 1 plus 2 plus right must equal 180. But the right angle is 90, so 1 plus 2 has to equal 90. So 1 plus 2 here is equal to 90. We have a straight line, and since 1 plus 2 is equal to 90, what's left over in the 180 degrees that make up this straight line angle at that point would have to be 90 degrees. And of course, that's true at all 4 vertices of the square in the middle. So we can see in this case, we've got a nice square of area C squared in the middle. And so that sort of seems like a good thing. And if we could somehow rearrange things here to get rid of the C squared and somehow make A squared and B squared show up, then that would be a good thing as well. So we start in the same way. We'll pick this one to be 3 and this one to be 3 from the end, or I guess 7 from the side. So go ahead and call that A and B. But let's suppose that we decided to swing this triangle down here so that it aligns with, I guess, its hypotenuse is united with the other one that's over in the corner. So then what we get are two of these triangles sort of pushed into this corner, and you do sort of a similar thing in the other corner. You'd have to do a little bit more rearranging to make it happen, but the idea would be in this lower left-hand corner that we go ahead and put these two triangles in there. So it would be sort of like sliding this triangle over and then rotating this triangle and dropping it down. Again, this would be length A, and this would be length B, B. This would be A, B, so this one would be A, and this one would be A. And we can see now that if this is B, then that length up there must be B as well, and if this is B, then that length over here must be B as well. If this is A, that's got to be B, and of course the hypotenuses are both C's. And the proof is really now one of visual recognition, and the way that you can kind of see this is if you try to play around with the area here, right? So there's 4 triangles in this particular configuration. And there's again 4 triangles in this configuration. And so in a sense, if the area here is equal to the area here, which we know it to be true because we started with 2 congruent squares, and the equal part in each of these areas pieces are these 4 triangles, those are equal. And what must be true is that the white space here would have to be equally balanced by the white space here. And so it's a matter of simply recognizing that what's left over when you take the 4 squares away is C squared here, and what's left over when you take the 4 squares away is an area whose size is B squared and A squared here. So this guy would be C squared in area, this guy would be B squared in area, and this guy would be A squared in area. So therefore, by equality of area in the 2 squares, we can see that C squared must be equal to A squared plus B squared, or just A squared plus B squared equals to C squared. And so we've proved the theorem.